Welcome back to Principles of fMRI. Today we're going to talk about the general linear model. We're going to start a sequence of modules on the GLM, one of my favorite topics. There are multiple goals in the analysis of fMRI data. As we learned before, they include localizing brain areas activated by a task, determining networks and functional networks that correspond to brain function, and making predictions about psychological disease states. And the most common use of fMRI is to localize areas of brain function. So the general linear model allows us to do that. And just to refresh you, where we are in the data processing pipeline is here in the data analysis part. And this is another view of a standard pre-processing pipeline where many of the steps are intended to prepare us for the general linear model, and we learned about some of those in pre-processing. The part we're going to focus on here is all in the box there in black. So it's the part where we build the design matrix and we estimate that design matrix, specify contrasts, and carry the analysis through to the group analysis level. The GLM is typically a two-level hierarchical analysis. This means that the two levels are a within subject or individual level and an across subject group level analysis. These are often done in stages. We do the first level analysis for every person and followed by a second level analysis. But hierarchical models combine those stages into one integrated model. The way it works is like this. There are several stages. First of all, there's a design specification stage where we build a model, and the goal is to build a design matrix. The second stage is the estimation stage, where we combine the model with the actual image data, and we estimate slope or activation parameter estimates for every person. And finally, we can do what are called contrasts, we'll learn about those soon, across different conditions within each person, and we can estimate contrast images for every person then, and those are taken forward to a second level group analysis. Once we do the group analysis, then we're prepared to make anatomical localization and inference about which areas are activated. So the first thing I like to do here is introduce the GLM family. And many people are familiar with various kinds of analyses, ANOVAs, t-tests, and the GLM family is a super category that subsumes all of those analyses. So the GLM approach treats the data as a linear combination of a set of model predictors or regressors plus noise or error that can't be explained by the model. The model functions are assumed to have known shapes, straight lines, or even known curves that are built in, but their amplitudes or slopes are unknown, and those need to be estimated. The GLM framework encompasses many of the techniques that we use in fMRI data analysis and beyond for data analysis more generally. So the GLM family is shown here in this blue circle, and many of you might be familiar with techniques like simple regression and ANOVA, and those we've put here as parts, or those I've shown you here as regions within the broader GLM family. So there's specific implementations of the GLM, and those are encompassed in a broader family, which is multiple regression, which subsumes both simple regression and ANOVA, and that's shown here in the blue circle. And multiple regression is a specific instance of the general linear model more broadly, which includes mixed effects or hierarchical models, we'll learn about those later, time series models that model autoregression, robust and penalized regression models, and others. And finally, there's another class, the broadest class, of generalized linear models in which we're allowed to have non-normal errors, binary outcomes or categorical outcomes, and logistic regression is one example of that. So in certain cases, simple regression, ANOVA, multiple regression, and some simple forms of repeated measures or hierarchical analysis, there is a closed form solution, an algebraic solution that lets us solve the problem in one step. But in many other cases, it requires an iterative solution, and we'll learn about those later on. So this is another view of the GLM family. They're all characterized by the presence of one continuous dependent variable, and depending on what the predictors or regressors are in the model, then you're doing different kinds of tests. So if you have one continuous predictor, you're doing a simple regression, one predictor, one outcome. If you have two continuous predictors, you're doing multiple regression. That's shown here in red. If you have a categorical predictor with 2 levels, like males and females, then you're doing a 2-sample t-test. And if there are 3 or more levels, the technique is one-way ANOVA. If there are 2 or more categorical predictors, you're doing a factorial ANOVA, and we'll learn more about those later. And all of these are examples of the general linear model. And what that means is you can create a set of GLM regressors that effectively does a one-way ANOVA or a factorial ANOVA design, etc. One other complication in the GLM that is important for us as we start to think about fMRI data is the idea of repeated measures. So in repeated measures, we're collecting more than one observation on the same individuals or units. So this means that we have correlated errors across those repeated measures. So let's say I'm sampling people after using a drug at time 1, time 2, time 3, time 4, etc. Those are all repeated measures, and the error terms then are correlated. And repeated measures analysis is one simple way of handling repeated measures and correlated errors in certain cases, but a more general solution that applies across many situations is this what's called generalized least squares. Is an iterative process of estimating what the correlations and the errors are and then correcting for them. And this is common in time series analysis. This is an example of a simple linear regression, which is a simple linear model with one predictor. And the stages are, first, we specify the model. In this case, the simplification of the model is that there's a simple linear relationship between the predictor and the outcome. Then we estimate the model, and here we're finding the slope of that line and the intercept. The next stage is inference. So we're going to test that slope statistically, which means we're essentially going to come up with a p-value. What's the probability that we'd observe a slope like this by chance? And then finally, a scientific interpretation. What does this relationship mean? And the regression model structurally, in terms of equations, looked like this. In vector notation, y is a vector of the outcome or the dependent variable. And that's modeled as the sum of several independent factors. One is an intercept, that's the constant term, plus, that's b here, plus the slope times the predictor value, that's m times x, plus the error or residuals. And the goal of modeling is to minimize the squared distance between the model and the data. So we're minimizing here the sums of squared errors, where e is an error term at every time point I, and y is the data. Y hat is the predicted data from the model. So hats are always used to indicate a predicted or estimated value. Here, in this example, the line, the regression line, I like to think of this as being pulled by rubber bands, vertical rubber bands that are attached to each point. So I've got 3 of those shown there, and you can imagine a rubber band connecting each point to the line. And the greater the pull, then the greater the influence on the line. So this is the structural model for regression, which is the basis for the GLM. And here I'm modeling y, the outcome data, or the dv, dependent variable, as a combination of the intercept, which here is beta naught, plus each slope times a predictor. So x's are going to be used to refer to predictors, and betas are used to refer to the slopes. So I've got beta 1, which is a scalar times predictor number 1, plus beta 2 times predictor number 2, and so on for as many predictors as I have in my model. And in matrix notation, this boils down to one simple, elegant equation. Y equals x times beta plus error. And our goal then is to solve for the beta vector, which is a series of regression parameter estimates, by minimizing the sums of squared residuals. This equation, y equals x beta plus error, is broken down in the following way. There's a series of y's, that's a vector or a column of y observations. And then the intercept is usually modeled with a column of 1s, which you see here, although it can take on any value. And then here you see each predictor as a column. And there's the observed data, y. The set of the intercept plus all the predictors together is called the design matrix. And that's a critical thing we'll be talking about in future future lectures. The series of the model parameters are what I'm estimating, and those are a series of beta values, from beta naught for the intercept here, continuing through beta 1 to beta p for as many parameters as I have in my model, plus a vector of errors or residuals. Now we'll go to an example of a GLM model that doesn't involve fMRI, just to illustrate the process. So the question here is, does exercise predict lifespan? This is made-up data, not real data. And what we'd like to do is look at the relationship between exercise and lifespan, controlling for other variables that may or may not be important, like, in this case, gender, male or female. So this is a plot of what the data looks like. And we see exercise on the x-axis, lifespan on the y-axis. We see a strong positive relationship. And we also see that females are different than males. So let's look at how we might model this with a GLM model. There's one continuous predictor and one categorical predictor. So here is our design matrix again and the structural equation. And the data would look something like this. So here's the lifespan data. That's the outcome across observations. And we're going to model that as a combination of an intercept, which captures the overall level of activity across the entire data set, or in this case, the overall average age across the whole data set, plus beta value times the exercise, which is continuous, plus a beta value times a regressor that codes for sex. So in this case, it's convenient to assign codes of 1 and -1 for males and females, or vice versa. And if we put that in as a regressor, that lets us estimate the effect of sex. So there's the design matrix times the model parameters, 1 for each parameter in the model, plus the residuals. So this is an example of what it would look like to model an outcome with a combination of one continuous predictor and one categorical predictor. And that is known as ANCOVA in the statistical literature. So that's the end of this module. Tune in for the next one where we apply this to fMRI.